morning and welcome back again to Intro to Geology. I hope everyone had a good time since our last lecture, and looking forward to moving on. We're changing gears again today. The topic will be different, and we'll be talking about not so much the specific origin of the ocean itself in the early history of the Earth, but we'll talk about the oceans, the ocean basins, the type of landforms that we've learned about in the bottom of the sea, and the old and the new techniques we've devised to try to figure out more about the bottom of the ocean. And we'll look at some of the sediments related to those ocean materials and some other, again, interesting things. I'll try to wrap up with something different about ocean basins as we go into it. For those of you who might wind up, again, as being an astronaut, I always kind of refer to a picture like this from space of the oceans, a pretty expansive kind of planet we live on with water. Again, most of our surface of this planet is covered with oceanic water, which is salty water, and it's dynamic just to see it from space. Here you can see the cloud cover, and even seeing right below the word ocean some pretty towering types of cloud systems that are there. Kind of spectacular, but you know, it hasn't been too long in history that we've really learned a lot about the oceans themselves in terms of particularly what makes up the bottom, the topography, the geomorphology of this thing. And when we think about the oceans, maybe some of us are in a different mindset. I've got a little kind of thing up front here to start out about,
Yo ho, a pirate's life for me. We pillage, we plunder, we rifle and loot. Drink up, me hearties, yo ho. We kidnap and ravage and don't give a hoot. Drink up, me hearties, yo ho. Yo ho, a pirate's life for me.
Things on television lately about Blackbeard and so on. And that was kind of the way we looked at the oceans. You know, where was the land, where was the water, and how could we get around on it? And we had all kinds of ideas about monsters that lived under the sea, and probably, in most cases, assumed the bottom of the ocean was one big smooth bottom barrel. Some areas they even thought that you go too far out in the ocean, you'd fall off the earth, kind of the flat earth society. Well, we've come a long way since that time in terms of things. I know when I was growing up, my idea about the ocean was kind of peaked a little bit by movies that I saw. This is one of the great big first movies about, related to under the ocean and what was going on. And it was way ahead of its time in some respects. Some of the things that were presented in this movie, actually, we now do. And have learned a lot about the ocean. If you ever have a chance, maybe go check this old, rent it sometime and watch it. It's kind of interesting. They've made subsequent things for that. But again, things have changed. Probably one area where we've changed so quickly and why we know so much about the oceans today, unfortunately, has to do with war and how, as we evolved on sea from sailing ships to powered ships of different types, the types of instruments that were devised and built to detect our enemy. Like, for example, trying to find the U-boats and where they were under the water and stuff. And of course, that goes on both sides of the thing. But once the war was over, the area of oceanography, particularly physical oceanography, really took off. And we took advantage of these tools that we'll make a list of here in a bit as to what is in the bottom of the sea. What is it like? Could we go down there? We eventually, of course, built submersibles, and today we're at the level where you can go down there in commercial submarines, thousands of feet below the surface, and see what it's like. Like in the movie The Abyss. A little cartoon on the left is kind of a schematic of the different kinds of submersibles that we've been able to dive to certain depths, and we can get pretty far down below the surface of the ocean. And we'll see some pictures of these later on. We began to drill the bottom of the ocean. We have some of these vessels there we can see that you can see some of the drill string piping on that bottom center picture. Helicopter pad on the one on the bottom right. And we would drill down and try to drill into the muds and the sands on the bottom of the ocean and eventually drill into that crystalline rock that made up the material below that, the basaltic ocean crust. A lot of different projects at one time in the 60s, we wanted to try to drill all the way through that outer crust of the earth and get deeper inside the earth. We never did go that far, but there are still operations going on in different parts of the world today to kind of bring that idea back. What about the ancient seas? What were they like? What kind of things lived in these oceans? We know that there's whales and octopuses out there now and a lot of things in our environment. But what about in the past? In the realm of paleontology, there are some unbelievable fossil finds we have of strange things that are now extinct. This is a fabulous picture off of a website, a gentleman here in Kansas who works closely with Sternberg Museum and some of the artist renditions of things that lived 60, 70 million years ago, 80 million years ago in these Cretaceous seaways out here in Kansas. So again, we not only want to look at what the oceans are like now, we want to do that to help us unravel the past. Take a look at things in our past, and see what they were like in terms of deposits and the fossil makeup and what that means about the history of the earth. Some pictures of some of the technologies that have changed. The one on the left, of course, an older picture about going undersea in this particular kind of device. You had to be lowered in on a cable, and you had this tethered, oxygen tank that went down there, and you were kind of still tied to the ship. Same with the one on the top right, except that, it's much smaller in size, and you could communicate with one another under the water. The one on the bottom right is a very specialized type of tool to go extremely deep when we're trying to work on say, offshore rigs and maybe along, extremely deep dams. The divers get paid good money to go down there today and work on stuff like that. But that one's kind of completely alone. You're not really tied so much to a cable. So what about kind of an outline now of some of the things, some of the instruments we've used and the ways in which we've mapped the seafloor? The idea from a more smoother bottom type of ocean basin to what we see now. And we've come, like I said, come a long way. And just in the last 6, 7 years, some new technology completely pushed us forward. Some old echo sounding profiles. We had a device that we could send a signal down, it would bounce off the bottom, kind of as an echo, and bounce back to some type of detecting device. Very, simplified type of instrument. We advanced that to where we could set some charges off or some kind of sound signal that would leave the surface of the ocean, go down into the sediments in the sea and reflect and refract off those layers and bounce back up to hydrophones and give us what we call seismic profiles of the layers of material in the ocean basins and the topography. Echo sounding is maybe more of a topography thing, kind of advanced fish finder, I guess, if you want to look at it that way. Seismic allowed us to penetrate into the layers and go deep into what those layers look like. In the last 20, 30 years, we've developed a technology called side scan sonar. It's a way in which we get a broader swath of information off that seafloor, a wider band, but we could also bounce radar off of those layers down there and give it a much higher resolution type of imagery. So everything got better and better with time in terms of ability to see the top, see inside, and just better resolution, better pictures. And when we start seeing all this stuff, what's the first thing we want to do? We want to actually go down there ourselves. Instead of dropping probes over the side of the ship or bouncing signals off the bottom, let's build some submersibles, little submarines, and go down there. And of course, sometimes the places are so deep and so dangerous where we might want to go, we don't want to put people in them. So we have a lot of unmanned submersibles. We'll take a look at a few pictures of some of those today. The most recent advance comes from satellite technology. We can put a lot of different instruments in satellites that can measure the surface of the ocean in terms of waves and temperature conditions and chemistry conditions and whether there's life in that water. But also a special device that deals with a gravity meter, measuring the subtle variation in gravitational attractions. And it turned out that image that we'll see in just a little bit here with satellite gave us the most high-resolution mappable device we've ever had for the seafloor. Came from NOAA. They had a satellite up there and they worked with other stuff. So here's some kind of cartoon pictures of some of these instruments. An echo sounder, just kind of, like I say, it bounces off kind of more localized in one area, whereas the radar gave us a broader kind of sweep of the area as we would go back and forth along the seafloor. Here's a seismic profile. In the bottom right on the inset, of course, you got a ship, and you have below the ship a kind of an energy device. In this case, it was an air gun that signal would bounce off the bottom of the ocean or penetrate through the sediments, so they both reflect and they refract, and they come back to these detectors called hydrophones. And you go through a whole variety of geometry analyses to figure out what those layers look like, and you end up with a picture like you see up on the top. Sea level would be at the very top above the word seismic profile, and here we see the topography on the bottom of the ocean with some of the actual layers in between. Below this, you're actually picking up on some ghost-like images. So you can process the data, but you have to spend more money to do it to eliminate ghosts. It's like working with your stereo to mess with the different frequencies and get that perfect sound for your ear. In this case, we know that those are ghosts, so we don't say, well, those are new layers in the bottom of the sea. Here's a picture of this new gravity anomaly map. This is taken by NOAA. Extremely high resolution of the seafloor. All the continents are in black. We're not interested in the continental values, so they were kind of darkened out. And this little inset you see over here over Asia in the top left-hand picture, we're measuring subtle variations in gravitational pull that result on the surface of the sea. Of course, there are waves that affect that topography too. But a lot of times the surface of the water, the elevation of it, is reflected by what the topography of the seafloor is. So by flying over an area, we exclude the wind patterns and the waves, and we're looking at those undulatory kind of images as a result of what the seafloor is. So really what we're measuring is the topography of the seafloor in this case. And so when you look at these colored areas out in the ocean, which they have names to some of these structures, of course, look at the detail in terms of what we see in terms of the structure, the shape, the alignment of those mountains and peaks and valleys and so on the seafloor. In the past, we didn't have that. We might go across one particular part of the ocean, have just that little narrow strip, then maybe another one. And this all started in the 1950s and 1960s. But we still, by the 1980s and early 1990s, didn't have we didn't go over every segment of the ocean with these ships. We had to guesstimate what was in between. Now, it turned out our guesstimations were pretty good, but we still had gaps. We still had some little missing pieces of puzzle. This picture with this gravity kind of filled in all the little voids. And of course, if we devise better resolution with this type of device, we'll find even more information about the seafloor. Here's kind of a drawing of the old view that we would see. We certainly knew about a flatter shelf, the continental shelf kind of topography. Then it would steeply drop off, go down the slope, and then hit the rise, and then get into the deep abyssal plains of the seafloor. But today, it's much more high resolution. That little inset there in the bottom right, DEM, I may have used that term before in this class, but DEM stands for digital, like a digital camera, digital elevation model. And so we'll take specific elevation points, put it into a computer, let the computer contour that information and show the resolution and detail of the topography of the seafloor. A digital elevation model is very, very accurate. In this particular case, they color-coded elevation values, and you can see this white line here represents the shoreline. This orange on the left, kind of a wider, flatter continental shelf, and all of a sudden we start getting these little kind of cuts down into the rise and the slope area of the continental margins. And I've got two arrows pointing to kind of two segments, one up here on the right, kind of cuts up a canyon, kind of looks like the Grand Canyon. If we could get all the water of the ocean, some places this would look like, driving along or flying over parts of the Grand Canyon. Pretty spectacular topography. That's in the California coast. Here's an image, again, created by a computer of a side scan radar database. Again, look at the resolution and detail of the topography of that undersea area. That was fabulous. I mean, if you're into Tom Clancy books, again, about hiding submarines in places, this kind of information would have been vital during a wartime scenario, and still is right now. We still utilize this information to work with that. Well, these are referred to as submarine canyons, just because they're under the sea. Take a look at the detail on this one. So again, our pictures get better and better. Now, as a geologist, I would look at that in terms of how do the sediments flow down those canyons when you have landslides, submarine landslides, or what area would we have in terms of organisms that live in this? What's the pressure? What's the temperature? What are all this, the conditions that provide, detail for sediments and life that live on our coastlines? Well, often associated with these submarine canyons that we've been looking at here are submarine landslides. And we may have looked at this early in the course in terms of a kind of sediment condition that we call fining upward packages, turbidity currents. Whether it's an overloading of some particular edge of the continental margin here, or a triggering by a vibration from a natural earthquake, and segments of material break loose and start sliding down that canyon, kind of funneling down the canyon, then they spread out into the deep sea, a big plume. Well, that mass of water and sediment material sliding down like an avalanche is referred to as a turbidity current. Once it gets to the bottom of the ocean, though, the velocity slows down, it spreads out, and the sediments drop. The heavier, coarser sediments drop first, then the finer stuff, and the finer stuff. Finally, the last thing would be the lightweight clays, the little flaky clays. And so in this little circle on the bottom right, the bedding style that we get will be a whole series of stacked, in this case about 3.5 pictures worth, of submarine turbidity currents. The current is the material moving. The deposit, we put an ITE in it, a turbidite. And turbidites have graded bedding. A big red star on it to kind of remember this characteristic of a submarine type of oceanic deposit. Turbidites are very common to deep sea types of deposits off our continental margins. Now, we could get turbidites in lakes, certainly in certain parts of the world, some active rift basin lakes like Lake Tanganyika or Lake Baikal in southeastern Russia. You can still get turbidite deposits, but most turbidites are a result of submarine landslides like this that have graded bedding, coarse on the bottom, finer, then boom, here comes another one, and another one. Kind of another cartoon of the same idea, an inset of a picture a diver took one time of watching this stuff slide down a submarine canyon. Here's a seismic profile of a submarine canyon that eventually got filled in, so we can understand the layering effect and look at the geometry and talk about the history of that. What happened throughout the history of this particular region? When we used to communicate across the oceans a long time ago, today you put your cell phone and pick it up. You can call anybody anywhere in the world. Bam, just like that. It might take a little bit of a delay, of course. You can send pictures back and forth and text messaging. In the 1920s, though, it wasn't quite that simple. You had the old crank thing on the wall and so on, and communicate between the United States or North America and Europe at this time, you had to have a big, long, solid cable draped across the bottom of the sea. Now, in this particular shot, you can see this ship that's at bay here. It's one of the ships they use to take materials and transport it across the bay. But up in Canada, draping across from the northern part of Canada, they would drape that cable all the way across the North Atlantic Ocean. And we had a pretty steep area up here. Well, it turned out there was some earthquake activity at that time. That earthquake triggered these submarine landslides, these turbidity currents, and this massive solid material went whipping down the canyon, the rise and slope, and just ripped the cables open, and bam, communication was out. Until what? Until they had to go back and take another whole cable all the way across the Atlantic. I mean, today if the phone goes out, it may be something like a power line went down in a storm or whatever, and in other ways. So the communication was, affected by a geological kind of phenomenon. Another side scan radar showing off the coast of Oregon here, these large slumping segments. So we can better understand the mechanics, what's going on different kinds of coastlines under our oceans by studying these topographic landforms. In the Gulf of Mexico, offshore, underwater, we can see these weird circular kinds of little pockmarks in the continental shelf. These are salt domes. Rising salt domes coming up. The salt dissolves out and the surface collapses in regions like this. So again, all of a sudden, because we can see better, we can make really good interpretations of what's happening off our shores. What kind of deposits are being formed. So here we have just a nice simple diagram of some of these topographic features. We have our continental shelf. It's very kind of flat. It's probably no more from 1 to 3 degrees of dip. A 3-degree dip may seem like a lot, but it's not. Our continental shelves are pretty horizontal in that respect. And all of a sudden, bam, you drop off on the continental slope. And as it starts to shallow out to the deep ocean, we call that the rise. It's called the rise because you're coming from the ocean, from the deep ocean, as you rise up to the continents. Then eventually you're out there in the deep abyssal plains, the flat regions of our ocean basins. And these are, of course, piles of sediment, of sand, silt, clay, and all the organic living things that are associated with that continental region in our seas. As we left those coastlines, here on the left side of North America, and head out, all of a sudden we see all kinds of strange little peaked mountains, referred to as seamounts, and then the seafloor starts to rise and get higher and higher, and we find these huge, long mountain chains running down many of the middle of our ocean basins. A mountain range in the bottom of the ocean. We never knew that. It was all this kind of research with these tools, these toys we had, to begin to understand the topography. Well, this right here, this image you see right here, was a breakthrough, a major change in how we understood how the surface of the earth behaved. This was something about seafloor spreading we'll get to a little bit later in the class. I'll spend more time on that. That brand new oceanic crust was being formed, and it was moving apart. And they said, oh, it's moving, huh? The ocean crust is moving. That must be making the continents move. All became plate tectonics. We'll come back to this story with an image like this later on. But I use this to show all the different topographic features. They have an alignment, a certain direction. Some are just little peaks. It's not that big flat ocean as we thought. And because we could see this, now we could understand the mechanics of the planet. What's going on this thin outer crust. In a few pictures later I'll show you. You can't see it real well in this picture because it's too far away, but running down the center part of any submarine mountain ridge is a small little valley, a little rift valley in there. We'll talk about that later on. I'll show you more detail. Here's that NOAA image again. So if you look at it, running through the middle of the Atlantic Ocean on the right here from Iceland all the way down practically to Antarctica is a mountain chain. If there was no water on this planet, if there was no water here, it would kind of look like that from space, just like that. Just imagine that there's no water now on the Earth. These are the continents, the highest spots, and all the rest of this is brand new topography to drive around in and go out there and hike and check this topography out. That's what the oceanographer wants to do, go down there and see that. Move around, collect samples, take pictures. So kind of some profile-like images across our ocean basins, these real high-peaked, things we call seamounts, the flat, deepest oceans. Here's on the bottom segment of the Mid-Atlantic Ridge, a rift system. This is what we saw. These are the images that we made in laboratories in the 60s and 70s. Say, man, we want to go down there. We've got to build a little submarine to go down and see what's there. I'll refer to some of these seamounts in a little bit about some other names we have with them, some things that change with that. For example, some of these volcanic seamounts actually rise above sea level, so they become islands like the Azores or the Canaries or the Hawaiian Islands. But some are under the ocean. When we first saw these with those tools, those toys, the echo sounders, we thought there were hundreds of thousands of submarines all over the seafloor. Almost a panic state the first time. No, they're just whales. And then they never moved. And they realize, oh, that must be some kind of rock structure down there that's got this big topography. So, just in 40 years, we've dramatically changed in understanding the seafloor. Some of those, like we have here, the seamounts, are right at, they come right to sea level, right across sea level here on the right. And some will have a very strange flat top kind of character, and I'll give you those names later on. Some have coral reefs associated with them, like these atolls, an atoll or an atoll. actually have kind of little circular coral reefs. I'll show you some great pictures of that. Some places on our planet, under the oceans, have extremely deep zones. In fact, the deepest oceanic trench in the world is over 36,000 feet deep. What's the highest elevation on a continent? Where is it? It's in Asia, right? Nepal and Tibet, called Mount Everest, okay? 29,000 feet, ballpark. All right, still rising up a little bit. But it's the relief, the difference between the highest and lowest spots is pretty spread out. If you go into the Western Pacific to the Marianas Trench and the island system there, it's 36,000 feet below sea level, and then you still have, right next to it, once you come above sea level, you got an island that goes even higher. So the relief, the topography within our ocean basins far exceeds what's going on continents. And that opens up eyes. All of a sudden you go, why? What's going on with this stuff? I mean, that's the excitement behind that. Kind of an evolution of an atoll. I'm not sure if the next picture shows that. I'm going to go back to this slide right here. Imagine that, kind of getting ahead of the case a little bit, that we know that the ocean plates are moving. They're moving away from those mountain systems, away from those rifts at different speeds, blinding speeds of 2-3 centimeters a year. All right? But brand new hot magma comes out, basaltic magma, crystallizes, gets hard, but it's still kind of warm overall. So something that's warm will be less dense, so it's kind of physically higher. That's why those mountain ranges are higher, because it's warm magma in this case. But as it moves away, what happens? It gets colder and colder and colder, so it gets denser and denser. What's going to happen to the elevation of the seafloor as it gets colder? It's going to drop down. It's going to move down. Now, if it's got a little island moving along with it in that plate, like one of these atolls, see all these little seamounts here on the right-hand side? This is a trench, so let's say this plate here is moving from right to left. It's going to go down in that trench. The sea level is going to drop and drop and drop, and those islands that are with it, they're going to take them with them. So they'll get lower and lower, and at some point you could actually do what with the island? Take it below sea level. It's not an island anymore. But right at the interface where the coral's trying to live and thrive in there, around that zone, that's going to change. So here's what happens in a cartoon kind of thing. Here we have that island, volcano, around in the top left-hand picture, okay? Got a little bit of a beach around it, around the edge of this, a small little beach. And then down here in B on the bottom left, the erosion of the island gets smaller and smaller, but a little reef system had formed. You got a little lagoon behind it, still got a beach on the island, but that reef structure, which depends upon the light zone and the surf to be able to thrive. So the only part of the reef that's alive is right by the water line, or a certain depth of water. You get way down, though, and it's out of the light system. That's dead now. So way down here, on the bottom right, that part of the reef is dead. And again, all of a sudden the island gets eroded even more. You got a great big lagoon, a much thicker, maybe wider reef. And eventually, where's the island? On the bottom right, it's gone. All I have is this circular coral reef system with a big lagoon, no island in the middle. That's an atoll. Okay? Here's some real ones. These little fringing reefs as things are changing. So in essence, kind of with this, the oceanic plate is moving further down as you go towards the top of the picture as time progresses and the plates move. Let's go back to this. If we look at this erosion, it kind of created a pretty flat, island, a little flat top to that system. What if sea level could rise very quickly and the plate's still taking and moving that down because it's getting colder? What you'll do is you'll drag down below sea level a pretty flat top type of old eroded island. Well, the name when it's like this at the surface, that's called an atoll. With the island, it's got a fringing reef on it. When there's no island, it's an atoll. When it's below sea level, it's called a seamount, a guyot. A flat-topped seamount is a guyot. If it's still pointy, you can call it a seamount. So under our sea, we have literally thousands and thousands of these little old volcanoes where magma is erupting from inside the earth, and it's at different stages of erosion and evolution. Off the coast of Hawaii, the big island of Hawaii, off the east coast under the sea, magma is coming up. We're getting a little buildup. In this case, the island is not there yet, but in the future, in the geologic future, that little place will be a new island. And if we're all still here, when it pops up above sea level, we'll have a new island to visit called Luihi, just off the coast. And what's happening is the Pacific Plate is moving over a hot spot, and so it's changed. I'll come back to what's going on with that process later on, okay, about the development of, that the hot spot stays fixed, the plate moves above it. So the islands all move with the moving plate. Another thing we learned, besides the topography and shape that I'll come back to with this kind of picture later on, is that when we brought sediments back up from the seafloor, from the ocean floor, we would age date them using fossils and other techniques. And it turned out that as we age date the solid rock or the sediments, the youngest age stuff, okay, the youngest age stuff was right where those mountain ranges were on the sea. Take a look again on the top, the right-hand side of the Atlantic. On Iceland, trace it all the way south. These are the youngest types of rocks, whether they're igneous rocks or whether they're sediments in that material. In the Pacific Ocean, in the eastern part of the Pacific Ocean, the red stuff represents the youngest thing. On the bottom is a scale for age. Red is the youngest, moving to blue is the oldest. And when we look at these pictures like this and age date this map, there's a pattern, there's a significant pattern. When patterns pop up in anything, doesn't matter what it is, you got to look at it closely. Why is that pattern going on? We'll come back to that with plate tectonics chapter later on. So the oldest oceans are out here. They're about, 180 million years old? The Earth is much older than that. So what did that mean? Yeah, I'll leave you with that question because we'll come back to answering that question later on with plate tectonics. Rocks on continents are much older, nearly 4 billion. 4 billion with a B. All right? Ocean is only 180 million with an M. That's a huge difference. That meant something in terms of interpreting what was going on with the mechanics of our planet. But it was evidence from oceanography, how we drilled these sediments and brought them back to the surface. Let me go back. Now we'll use this map. See these color patterns in here? Notice that they're offset. There's kind of a break, and they kind of show a few black lines in here. Well, that offset, something was going on mechanically with that. There was faulting. There was fracturing going on in the seafloor. So we realized they were from rift systems and transform faults that were developing. So not only did we see topographic features, we see evidence of the same thing we see on the continents. Crust ripping apart and moving sideways and moving up and down. Here's another picture of one of those rift systems close up with a DEM on that. Central ridge is high, is elevated nice and high because it's warm and buoyant, less dense. These are the mid-ocean ridges. Bam, all of a sudden they're offset right there at 90-degree turn. What's going on with that? How can you rip that and slide that? And we'll come back to that, but that has a name. It kind of offset. It's called a transform fault. Well, I'll define a transform fault again later on this semester, but all of a sudden we create new terms in our vocabulary because we're learning more about the seafloor. So it's faulted. Here's probably the most unique, coolest looking image of a seafloor, mid-ocean ridge with a transform fault on it, a series of islands up in here, whole mixed bag of goodies. So what's down in those little cracks, those rift systems in the ocean bottom? Okay? Obviously, we've got ocean crust. This gray stuff up here is supposed to represent basalt, real young, brand new, fresh basaltic ocean crust. And we can get submarine erosion, pretty steep-sided fault structures in here. You can see these black lines represent faults. The arrows are in white, showing relative displacement. So when that moves and fractures, you'll get submarine landslides falling down into those rift systems, into these little valleys. So sediment begins to pile up in there. And at the same time, you keep having magma ooze out. Magmatic material, in this case basaltic magma, these red blobs, coming out in the bottom of the sea. And of course, we came up with these ideas by all the stuff we collected, dropping, big dredges over the side and pull samples up or core them and bring them up. But we hadn't gone down there yet. We still hadn't gone down to the bottom of the sea. So we said, let's do it. They built a little submarine called Alvin, not the chipmunk, okay? Real thick-walled special device at Woods Hole Oceanographic Institute. There's an acronym on your screen, WHOI, W-H-O-I. W-H-O-I stands for Woods Hole Oceanographic Institute. And this is in Massachusetts, in Woods Hole, Massachusetts. It's one of the major top 3 or 4 oceanographic institutes in the world. And Alvin was built specifically to join up with some French researchers and go down at the bottom of the Atlantic and check it out. What do we see? The first time they went down, they got stuck. They spent all their time and energy trying to get unstuck so they wouldn't get stuck down there and die. Because they just drop and suspend. It takes them hours to drop to the bottom of the sea. It doesn't take too many people in here either, by the way. You can fit 2 medium-sized to large-sized individuals. 3 real small people can fit in. That's it. And you just sit there and you drop. You release your ballast and you just sink. You come off the old mothership Lulu. You head on down in there. Okay? These are some test dives they were doing on the Bahamas before they actually went down in. And then you got all kinds of devices, cameras and big operated claws. You can grab samples and put them in baskets and bring this stuff back to the surface. When they got down there, boy, were they full of surprises. We saw strange things we never saw ever in the history of science. We saw these big chimney-like things that were belching out clouds of smoke, just blowing out of there. Black, yellow, green, white, all different kinds of colors. First time they stuck the temperature probe into the smoke, the chimney, it melted it. It was that hot. He had to redesign a brand new thermometer, so to speak, to test this stuff. They saw right next to it all kinds of strange, organisms living in contact with this. They said, we got to tell our biology friends. There's all kinds of new life forms down here that had never been, defined. Now you've seen this early on in the semester about how you get that rounded bulbous shape of submarine lava. Remember we talked about that, submarine lava? It gets that rounded top to it. Whoops. A photograph from the first trip. See that rounded stuff? Lots of brand new magma. And so in some places they could see activity, some places nice and quiet. Nothing going on down in there. And we're talking 8, 10, 12,000 feet below sea level in that little sub, crammed in there, collecting this data. It must have been not only, besides exciting, kind of almost spooky sometimes. Am I going to get back? Yeah?
What is the deepest man has been able to penetrate?
I think around 12 to 13,000 feet, I think, but I don't have that at the tip of my tongue right now. I'd have to look it up. That's a good question. Because there may have been some newer dives more recently going on, but it would be a goal. They hope to go down into the Marianas Trench, 36,000 feet. They do in the books, but like Clive Cussler and some of those books, but not yet. When they went down there and started looking at the drilling material, and they were looking at the pictures they were taking and the samples they brought back, they said, there's kind of a sequence of rocks down here, a certain package. I've got basalt, I've got pillow basalts, I've got on top of that these strange sedimentary layers that are quartz rich. I've got organism fossils in it. I even got some kind of columnar basalts they call sheeted dikes up here. Strange whole package of what makes up all of the oceanic crust. In our vocabulary for you right now in this class, the word ophiolite. The word ophiolite, all you have to remember is that an ophiolite is what makes up all of the ocean crust material, from the bottom to the top. And it includes the sediments and the fossils that are on the top, which are quite varied in their character. So an ophiolite suite, so to speak, an ophiolite package is all of that stuff. Now I tell you that because we found that a lot of ophiolite packages of rocks we find on the surface of the earth or on certain islands are really full of money. copper, nickel, special metals. And by the way, have played a major part of history, going from the Iron Age to the Bronze Age and so on, and slavery and, changes of historical things because of these ophiolite deposits, because of that smoker. Remember this picture early on in the semester up in Upper Peninsula of Michigan? These are metamorphic rocks right now, but these are old pillow basalts in the middle of our continent, an old leucogen, as I talked about earlier. But this was erupted under the sea at one time. What else did they find? You like clam bakes? These clams are huge, 18 inches, 20 inches long, one clam. And that black stuff in the picture, that's fresh basalt. So living down here in 12,000 feet, no sunlight, all these organisms, fabulous stuff down there, where'd they come from? I had to go back to the drawing board and say, what's going on down here? What are our ideas on the, quote, origin of life in a scientific point of view? What's happening? It wasn't just these big clams they saw. There's the clams in the top left. Here's a sea anemone in the top right. Look at that big kind of spider-like crab. The thing in the bottom left, huge tubes, big kind of white sheathy-like tubes, and sticking out of it was this fleshy red thing. You touch the tube and it just pops it. Big worms. These are big pagoniforan worms. There's another picture on the bottom right-hand side. In the center, all that yellow is sulfur. Over here in the right center part, this is pyrite or fool's gold. Iron disulfides, a lot of sulfur. A lot of bacteria down here. In the bottom center picture, close up under scanning electron microscope, these little zigzaggy lines on this crystal of a pyrite is a type of bacteria. They're sulfur-eating bacteria called desulfuricans. So there's a primitive life form down there, and next thing you know, you got a food chain. It gets more and more complex all the way up to these great big, clams. We never knew these things existed on the planet. And the biologists now are going down there and find more and more and more of these extremophile type critters. Would they help us understand, how to deal with things? Or they have certain chemistries that would help us understand and maybe heal cancers and whatever? A lot of interesting new stuff going on. Now let's see if this kicks in. On the bottom left you can see a smoker stuff going on. And when that kicks, on the right-hand side there's a crab crawling in one of those worm tubes. And if it kicks in, I hope, watch what happens when the crab touches it. Boom. So these crabs are picking food off of it. Huge ecosystem. Big symbiotic relationship of these things under the ocean. So if you want to go into something fabulous, physical biology in oceanography realms is just something that's just exploding in terms of jobs, and it's just the stuff we learn about it. Quite fabulous. So under our sea, we've now learned about, by going down there and collecting things and taking pictures, all these strange biocommunities, these chemosynthetic. It sounds fancy. Chemosynthetic. They're just thriving on each other. The chemistry, but no sunlight, no photosynthesis. And that's not what we normally thought of 40 years ago, 50 years ago. Here's a map of the world. And so we got these hot water vents I showed you pictures of, the hydrothermal vents. We also have places where the organisms can be found where super salty water is kind of oozing out. Salty springs coming up at extreme depths, these hypersaline, ultra salty seeps, so to speak, where we find these same communities. Or where oil, organics, gas and oil are seeping out. We find the same thing. And even where these crustal plates are colliding and subducting and they're squeezing like a giant squeegee and water's oozing out with different chemistries, we're finding the same biocommunities in subduction zones. So the ocean is really full of surprises down there. It's a really cool thing. So I remember some of these. This would make a good question I could work with, some kind of multiple choice type question, I guess. So it kind of looks like a multiple choice question sitting on the screen. So here's some hypersaline seeps, Florida on the left, way off in that deep area, way down here, water's oozing out, and a little biocommunity of critters down there. these extremophiles. Here's some offshore of Texas and Louisiana. Kind of a hydrocarbon seep, or the organics of oil oozing out. Off the or Oregon coast up here, a subduction zone with a Juan de Fuquen type of trench. So what about sediments then in the ocean? What about kinds of things that are being deposited that make up part of this ocean basin process? I'll go through a list of sediment types here. Those that come off the land. Deltas wash a lot of stuff into the ocean. Wind, of course, can blow things into the ocean. So anything derived from the land is referred to as terrigenous sediment. If it's something that's derived from a fragment of a shell of some organism that lives in the ocean, marine organisms, things that are alive, plants or animals, corals, clams, lobsters, anything that's got a hard part, okay, but is referred to as biogenous. And those that just do a purely chemical precipitation process, a crystal of salt precipitates out of water, or gypsum precipitates out of water and sinks to the bottom, no life involved, nothing blowing off the land, just happens right there in the seawater because of the temperature, pressure, pH, pH conditions, okay? That's referred to as hydrogenous, or in some books, abiotic, meaning not biological. They're just purely chemical precipitates. So three major kind of styles or types of sediments. Those from the land, those that are in the ocean. The last two are in the ocean. One's living, the other one's not. So here's a picture of the Mississippi Delta, so you can see lots of stuff being flushed out into the oceans. Here's a coral reef system with lots of critters, fish and the corals themselves and so on. When their skeletal remains drop to the bottom, they become part of the sediment. Here's some pictures we saw early on of plankton, the shells of, these that make up that mucky bottom they call ooze. There's forams and radiolarians and diatoms in all these pictures. And I think I showed you these pictures like this in the chapter on sedimentary rocks. But there's something else down there that we found. Strange little grapefruit-sized, softball-sized spheres, little balls, okay, manganese nodules. Manganese is an element. But if you cut one of those manganese nodules open and do a chemical analysis, it's not just manganese. There's nickel, copper, zinc, occasionally a little bit of gold, maybe a little silver, metals. Valuable metals, these things probably formed by ocean currents moving these metals that are belching out of these rift vents, and they get nucleated and they form a little spherical body down there. They kind of precipitate as little kind of jawbreaker type things, or concentric rings inside of them. That's a high concentration of money and ore. But how do you get it out? Way back years ago, I remember seeing these kind of cartoon renditions of a ship with a giant vacuum cleaner in the back to suck them off the bottom and then pull them up and then process them. And they're all over in different areas on the seafloor. Okay? We need technology to get them if we need them. But the big question is, who owns it? Who do they belong to? You want to be a lawyer? Get into international law about mineral deposits on the bottom of the ocean. At one point in the 1980s, when President Reagan was there in Congress, they passed a law. Okay? And they developed something called the EEZ. Remember what the EEZ is. It's called the Exclusive Economic Zone. So anywhere on our country shores to a certain distance out, kind of like we do with fishing industries, any of our territories, that certain distance out you see on the map, that's us. That belonged to us, what we said. Well, do you think the rest of the world said, oh, okay? No. Right now, this is still in the court cases. International law arguing who owns all these metals, who owns all of the oil and the gas and the fish and all of that, all those natural resources out there. The EEZ. That'd make a great question for making up other kinds of EEZ words. Elvis, exclusively Elvis something. I don't know, I'll make something up. But remember what it stands for, exclusive economic zone. It has to do with these natural deposits that we claim, belong to us out there. Well, recently we found something else out there. On our continental shelves, we've been noticing that there are some little pockets. When we do drilling, we've noticed some little pockets of this solid stuff referred to as methane hydrates. Methane's a gas, but this stuff is hydrated, and it's kind of a solid material, a crystalline stuff, kind of like ice. Kind of like dry ice in a way, I guess, if it's not CO2. This is a methane gas hydrate, and little pockets and zones of probably material that was from organics in the past. It came altered, converted to that, and then under extreme depth and pressure and cold temperatures, it got converted to this hydrated process. If you can get that out of there, you've got an energy source that'll burn clean, and there's so much of it on our continental shelves, it'll last a long, long time. Now, we know what oil costs today, and other gas products that we're paying for, and all the political implications with that. The only bad part about it is it's extremely volatile. It's extremely volatile. No one's really devised a perfect recovery mechanism yet in drilling, because sometimes you can cause it to disrupt and belch out, and these gases would be released. And I don't know if you know, but if you ever got a lot of bubbles coming up through water, a lot of air bubbles, gas bubbles, and there's a boat sitting there, the boat's going to sink, which, by the way, has happened. And we probably think has explained a lot of disappearing boats in some places like the Bermuda Triangle. Releasing of gases, a natural release, not us going in there and causing an explosion or breaking it loose or something. Has this methane gas been released at a certain rate recently to maybe be a reason why we've had global warming? We don't know. We're looking at it. Possibly. That's what you got to do as a scientist. Has it happened in the geologic past? When it releases and belches out and breaks loose, does it cause a huge submarine landslide? Which therefore could cause what? A tsunami of some sort. We don't know. But we're looking at it. We're trying to tie and study these things together to figure out what's going on. So there's a drilling danger. If you have the ability of engineering, you want to make a lot of money. Whoever first devises the way to get this out of there, off our continental slopes, easily and safely, you're going to be very well off. Very well off. Because there's a tremendous amount of this material down there. Clive Cussler wrote a book called Fire Ice. That's the methane hydrate, fire ice. And in the book, in the drama of the book, they talk about people trying to purposely release this to cause tsunamis, to go across the Atlantic Ocean and hit Washington, D.C., and kind of a political implication thing in terms of terrorism, I guess. But but it's a product that's there. Here's some more pictures, but the pie chart I want you to look at. The pie chart, the green are all the fossil fuels in terms of amounts. Look at gas hydrates. Fossil fuels, it's just amazing in terms of organic areas. The organics on land, the fossil fuels, oil, gas, coal. Look at the gas hydrates. These things burn clean, so no pollution with it, if we could just figure out how to get it. So oceanography has come a long way. Here's an old picture of the Navy. This is one of the first submersibles. They built this to try to go find and get our sailors out of submarines that sunk to recover their bodies. They'd go into very deep water. They wanted to get them back. The Trieste, kind of an interesting thing. And there's a gentleman, you'll probably hear in just a bit here, you'll know, who got involved in one of these. But today's submersibles, I could show you hundreds of pictures, all kinds of new goodies. From these unmanned ones to the ones you can go down into commercial ventures, and I don't know what you pay to go down there, but you can get pretty deep now in a submarine. It's all big, thick glass. You can see everything around you. Pretty spectacular. And it'll become more and more commonplace. Someday in your future vacations, if you can afford it, you'll see some stuff you just can't believe in life. They'll take you down some of those trenches, just like in the abyss, down in the Caribbean. They do have one now that gets down about 1,500 feet, 2,000 feet. That's pretty deep. So, kind of cool. Here's some more of the Alvin. You can log on to a website, get into a little kind of screen. You can go 360 and rotate around, look at the dials that are part of the Alvin makeup. On the top left, this big ship, this is Lulu. Lulu is the mothership that brings it out, and they drop it in the ocean, and they take off and go into their dives. But here's some other new ones being developed. Manned and unmanned. All the different countries are involved in this. Now, I think you can get an idea where I'm going with this particular picture. Bob Ballard. Remember Robert Ballard? Robert Ballard was in the Navy. He was an oceanographer. He didn't become really super famous until what? Till he found the Titanic. Going off and looking for the Titanic. But some of the research that he has done and what he continues to do in education is absolutely amazing. Bob Ballard came up with this thing called the Jason Project. Jason's the name for his little unmanned submersible with cameras and stuff on a tethered machine that goes in there and he can rotate it around. The Jason Project in education is for middle school and high school kids. There's different areas all around our country that you go to, and the students go there in a great big room with giant screens, and they have live connectability right there to a research team every spring for 2 weeks. They go to the Caribbean, they go here, they go there, and then these kids get to talk live to the researchers, ask them the questions. They see the research going on right then, and the purpose of it is to get people interested in science, to see what's going on in our oceans. You know, yes, space is out there, and I don't want to put down space. A lot of money and talk going on, but oceanography, we're right here, right now. We need to know more about it. So look it up someday about, and I've got the website on here, and it's rather lengthy. I don't want to click to it and go to it right now, but some pretty spectacular stuff. I could spend a whole hour on this and what might have happened at Fort Hays in Tamanic Hall back in the 90s. I had talked with Bob, and we were trying to get a Jason Project site here on campus. It didn't happen, but one never knows. So here he is. He's heading out to go find the Titanic in the North Atlantic. And here's kind of a drawing, a picture of Alvin and their little submarine. Here's some of the first pictures. The bottom left's the first radar detection they found from the surface. Oh, there it is. Let's go down there and find it. And these are the first pictures they ever saw of the Titanic. Pictures on the top, 1986. Picture on the bottom, 2004. Now, if we had time and looked closely, you'd find out that things are missing. It's not just one group of people looking, there's another group. Some groups who want to take stuff back and sell it. And so there's a huge kind of argument going on now as to whether they should leave that alone or bring it back, and I'll leave that to the philosophers and other classes right now. But we're learning more about the sea.
There's a Claude Cussler book called Raising the Titanic.
I know. Yeah, it's wild. Here, this is Jason, the little robotic thing that Bob Ballard kind of devised to go in and take pictures, or you know, where it's maybe more dangerous to go into. So you get down there, and all of a sudden, you start thinking, what else is there? Look at this. A picture of you go, okay, good, it's a fish. Well, you know, until 1950s, we didn't know. We thought this thing was extinct, till somebody brought it up in a fishing net. This is a coelacanth, but they're in the deep sea, places we never got to until more recently and more often now. It's like having, when you see a lot of things on the news, there's always maybe somebody's got a cell phone or a video camera, you got pictures, bam, of all kinds of stuff happening. Now we're learning more about the seafloor, and we need to, there's so much to cover. Look at that thing. Fabulous. But they can get pretty bizarre looking too. You can get on the web, it's amazing what stuff we're finding now that we had no clue was here. New species of stuff. And yet it's also cool looking. Some of the things about this luminescence and things that we see down there and what's going on biologically just kind of blows the mind. Look at the fish in the top right. You could do funny TV ads, or you know, unfortunately probably you see these things in the next, you know, monster movies of some sort, but you know, strange things. A lot of wild things down there in the bottom of the sea, so.
Alive! It's alive! It's alive!
The Titanic